Hello colleagues, we will continue now with basics. We just realized one more time that people don't read our manuals, so we will guide you guys a bit more carefully and, let's say, deeper. And today we will discuss MF NIA, NIA and IA. So what are those? It's a multi-frequency, non-inverse architecture, inverse architecture, IA, IA, and non-inverse architecture. What are they? What the difference are, and which one to choose? Now, your main page is this one. So you go to Downloads, and then you choose the architecture comparison. So in architecture comparison, you see non-inverse architecture, inverse architecture, and multi-frequency non-inverse architecture. They are placed like this because historically they were developed like this. First one was this, and then this. There is a short summary. You can read them, but basically the whole video is about their comparison between these three architectures and in which cases which to choose. Now let's start with the most basic, and this is why when you are not sure, we always recommend start with non-inverse architecture. Why? Because with non-inverse architecture you have the least number of possibilities to make a mistake. It stems from the fact that this is the simplest architecture. How it is arranged? Now, like in any our indoor GPS systems, there are three major blocks. One is stationary beacons, so these are the stationary beacons. Mobile beacon, which you place on the object. It could be person, forklift, robot, drone, anything moving. And the modem. Modem is central controller of the system. Everything is described here, so you can see all these nodes. It's the central controller of the system that is basically commands everything. Who is talking to whom over radio, at what time, it collects the data from the beacon, it sends the data to the beacons. It also connects to your system. It could be a dashboard where you see the tracking, or it could be your robot, for example, which will be getting the data from the system. But you can connect your robot, and mostly people connect the robot directly with the mobile beacon because it's better and faster, and we can discuss this a bit later. But otherwise, again, three major blocks. Stationary beacons placed around your building, warehouse, assembly plant, factory floor, whatever area, mobile beacon, and the modem. Why it is the simplest? Why the non-inverse architecture is the simplest? It's simple because it is using only one ultrasonic frequency. As you may remember and know that we are using radio for very precise clock synchronization between the beacons with the help of the modem. This is why the modem is a kind of your atomic clock. Of course, it's not atomic clock, but it's serving the same purpose as their atomic clocks, or let's say as the ground station and the atomic clocks on their GPSs. So the ground station doesn't correct those atomic clocks, but we don't have atomic clocks. Our system is significantly less expensive than GPS satellites, but we need to synchronize them all the time. So the modem's responsibility is this, synchronizing all the beacons. From this perspective, non-inverse architecture, inverse architecture, and multi-frequency inverse architecture is principally the same. So the modem is synchronizing, getting data. It could be slightly different format, but it doesn't matter. So details doesn't matter in this case. What it does is synchronize. What does matter and what does differ is marked here in pink. So in non-inverse architecture, all frequencies that beacons are using is the same. By default, we are using 31 kilohertz. But it could be other. But the point is, they are the same. And you can compare with inverse architecture. In inverse architecture, it's in principle different. In inverse architecture, their frequencies are used by different beacons are by definition different. So 19 kilohertz, 25 kilohertz, 31 kilohertz, 37, 45. As you see, there is 6 kilohertz step between them, because we need to receive all of those frequencies at the same time and being able to separate them from each other, because we need to receive them simultaneously. It's a pretty difficult technical task, but since we have digital filters inside, we are capable to do this. But this makes inverse architecture like 10 times more complex. Not only because of this, but this is already enough. Because in this case, you kind of receive only one frequency at a time. In inverse architecture, you receive at least 5 frequencies at a time, and it's very, very difficult to filter. It's very, very difficult to choose which one is one, because they look the same. And when one of the beacons is very close to, for example, one of the mobile beacons is close to one of the station beacons, then even filtered out wrong frequency can be heard very much like the right frequency, which is far away. No, because the dynamic range of the filter is also limited. But to make the complex story short, inverse architecture is very, very complex, and the biggest difference is, in terms of implementation, is that we are using the same frequency for non-inverse architecture and different frequencies for inverse architecture. For you as a user, the biggest difference is slightly different. What it is? Who is emitting ultrasound? In non-inverse architecture, the mobile beacon is emitting, so producing these fast clicks. You cannot hear the ultrasound, but you may hear in the quiet room, like I'm sitting now, clicks. In inverse architecture, the stationary beacons are emitting ultrasound, and their mobile beacon is receiving. So by default and by design, the mobile beacons in inverse architecture are absolutely noiseless. This is why inverse architecture is recommended for people trekking, for example, because quite a few people want that something is ticking on the shoulder. No, if you have a badge, it's absolutely listening badge, it's absolutely quiet, and the station beacons, which are whatever 10-20 meters apart. Okay, first of all, you cannot hear on such a distance. Second, who cares? They are there, particularly in the industrial applications. So this is why if noise, or let's say even the slightest noise is important for you, then inverse architecture is your choice and non-inverse architecture is not. But the biggest difference as a result of this is the following. Since you have more than one, or when you have more than one mobile beacon, in non-inverse architecture, since we are using only one frequency, you can serve only one mobile beacon at a time, because the frequency is the same. You cannot distinguish based on the frequency. And unfortunately, we cannot distinguish the mobile beacons from something else, like code modulation, for example, or some special other modulation. No, it's the sensors are resonating, so they are very efficient in terms of emission. This is why the beacons consume so little power. This is why you can run them on the battery. But the drawback, you cannot modulate the signal very much. So this is why at a time you can track only one mobile beacon. And then after a fraction of second, still, 8 hertz, so like 100 milliseconds or even less, 50 milliseconds, but still not simultaneously. You can track another one, then another one, then another one. But when you have like 100 mobile beacons, it means that 1, 2, 3, 4, 5, 99, 100, 1, 2, 3. So the update rate per mobile beacon with non-inverse architecture drops. So the biggest advantage of non-inverse architecture is that it's very, very simple. The biggest disadvantage of non-inverse architecture is that the update rate drops proportionally to the number of mobile beacons. With inverse architecture, this is not happening. With inverse architecture, the stationary beacons are emitting different ultrasonic frequencies at the same time, and the mobile beacons are receiving those beacons, receiving those signals from different beacons, and the mobile beacons, they themselves calculate the position. And you can have whatever, 1,000 mobile beacons, theoretically, and they all will calculate at the same time, and the update rate doesn't depend on the number of mobile beacons. This is the biggest advantage of inverse architecture, because you can run, and you can see our videos on YouTube where we run whatever 100 mobile beacons, and the update rate is the same as with one. This is the biggest advantage. But disadvantage is that your mobile beacon is receiving ultrasound. And for example, if you have a drone, and drone is very noisy, so you cannot place their very sensitive and receiving ultrasonic frequency beacon on the drone, and the drone would fly. No, it will not work, because the noise would be such a loud, even audible noise, but it will go to ultrasound as well, that it will block the reception of the ultrasound signal from their stationary beacons far apart, and their working distance would be not 30 meters like typically, but rather to a few meters. How much of you? It totally depends on the conditions, on the noisiness of the drone, on many things. But it would significantly drop. So this is why for very noisy objects like drones, we do not recommend inverse architecture. It's for people tracking. But there is an alternative, means kind of in the middle. Okay, what if we have mobile beacons with different ultrasonic frequency, 19, 25, 31, 30, etc. So in this case, the mobile beacon will be emitting ultrasound, and we can put the mobile beacon on something noisy, like a drone. But in this case, since we have 5 different frequencies, our super beacons are able to distinguish between their different frequencies, and as a result, between different drones. So it means that you can fly up to 5 drones without update rate reduction. And this is why multi-frequency. So it's like NIA, it's exactly like NIA, but it's like 5 different NIAs at the same time with the same number of beacons. So you don't need to install more beacons. No, the same beacons, but 5 different frequencies. So you get the MF NIA license, you enable, and then you enjoy high update rate. If you have more than 5 drones, then yes, the update rate will start, reduce, but 5 times slower than with NIA. So, for example, for 10 drones, you will have only half speed reduction, and with NIA it would be 10 times speed reduction per drone compared to the whole system. So, for example, for you have whatever 10 hertz, and with 10 drones. For NIA, you have only 1 hertz per drone, and with MF multi-frequency NIA, you will have 5 hertz update rate. So hopefully that was useful for you. If you have additional questions, please ask to info@marvelmind.com, and we are always happy to help.